All right, so this is just quickly to show my clock module that I just finished building up. I don't have all the pieces that are so nice as Ben had them. For example, I couldn't find a small potentiometer, so I had to use this big guy. But other than that, I didn't have that switch actually. That switch from his website, from his parts list, was pointing to a sliding 3-position switch. And so when I bought the pieces, which I have to do in a city that's sort of like 2 hours away from here, and nobody had even a sliding 3-position switch, and unfortunately that's actually dumb, because really it was just a 2-position switch that is required, and so ultimately I found this here, which is really dinky, and I'm gonna replace this. But as you can see, I actually made some modifications here, and this is really all I want to quickly state, because I'm thinking of ergonomics. So this is all going to be part of a front panel at some point, and I find it makes more sense to have the light. So if the automatic clock is running, so I can monitor the automatic clock here, which maybe this wouldn't even be part of the front panel. But as you can see here, this is the resulting clock in green. And if I use the manual clock, then I have this direct monitoring diode for the manual clock, but the manual clock pulse doesn't go through. And if I put this switch over here, then the automatic clock is turned off, and so now only the manual clock is turned on. And I think it makes more sense to have a red light for this, because it basically says the machine stops until you go into your debugging single step mode. And I just watched a video of another guy. Gosh, I'm bad with names, I'm sorry. Who recommended to actually increase the capacitor here, and in order to have the manual clock cycle be longer. But I don't know, I don't think that's an issue with mine. As long as I hit the button, it has the pulse on high, and if I release the button, it goes on low. Maybe I made a mistake here. Maybe I have to review this. But then the other thing that I did is the halt signal. I still use the 3 chips design that Ben uses. I might be changing that to using NOR gates, especially because I made some modifications here. I'm using an additional inverter here, because I want a red light that signifies the halt condition, and I can emulate this or simulate this simply by taking the input for the halt condition off the ground. It was tied to the ground, and if I take it off, then automatically it will be detected as high. And so if the halt signal was on, then this would be what the user would see, which makes, actually it would probably be this, because automatically the computer ran into the halt condition, and this is nice because it tells me in red that the computer is currently on halt. And at this point, I can then switch it into manual mode, and I would give another clock pulse, which then would continue to the next step, which then should clear the halt condition, and we should be able to just manually continue stepping or put it back into the automatic mode. So that's really all I had to say about this. The clock module is really not the big thing. It's not the computer yet. of course, I played around a little bit with the frequency divider, and I play a little bit around with sound, so I have some fun, and I guess I'm gonna see if I can demonstrate this without wasting too much time. It's really hard if you have to hold your cell phone with the other hand. I guess now I already wasted people's time, so I better get this going. I better get this running. And actually, I don't even have to mechanically connect these two. I could just, gosh, we're getting all fuzzy. Okay, so now these two boards are put together, and so now I would just have to connect them, and I hope I have the pieces for that here, so I can. What I wanted to say while I do this, it's kind of really interesting that Ben Eder, I mean, he obviously is an educator and a professor, I'm assuming, in computer engineering, and he is doing just a marvelous job. And I don't have the right colored jumper here, but I'll just use the blue one to connect these two boards together. And what is very clear is that the stage of building that clock module is sort of really to get it's the step one of doing everything else, because you kind of sort of debug your own skills in breadboarding. So what do I have here now? I have to connect the clock input here with the clock output. That was from a stage when I didn't have the manual thing yet. So what I'm gonna do is, all with one hand only while holding my cell phone, I have to take out that wire. Oh my gosh. And how do you do this with only one hand? It's crazy. You just have to get your fingernails under it. Okay, so now we have that. And so what is this? Why is this connected like that? I think this was my reset. That was a different demonstration that actually I can still make. So first thing I have to do is I take the output, the final output of the, let's see, where's the final output here? This is the final output of the clock, and I put that into the input, which I believe this is the reset side. This should be it. Yes. Of the counter. And you might, if you fast forward on Ben Eder's thing, and this is the micro instruction counter that he built, which is really just a frequency divider. And there is some fun to be had with the line decoder, where you get these 8 LEDs. And so what I can do now is I also have a little amplifier, because my entry into electronics was analog, and I always like to play around with amplifiers and sound. So here's my transistor with the, let's see if I can get this sharper. My transistor with the bases, the base and the collector, and the here's the collector tied to the +5 volts, and here's the base with a little resistor, so I can connect here to the base, and here's the speaker. So if I connect just the just the clock output, I mean the clock input now here, see, and as the clock ticks, I'm hearing ticking sounds, so it's like a real clock, it ticks. And as I turn up the speed, my speaker starts to give squeezing sounds. And there's a fun part in this, that as the frequency divider divides the frequency, I have different octaves. So for example, this is already 1 octave down, another octave down, another octave down. So that's one fun part of it. And now I'm taking this down. Then another thing that I found interesting, just to play around with, maybe I don't even need that speaker anymore. It's just like one funny thing. So I disconnect the speaker, the whole amplifier circuit here. And what I'm going to do is I take the reset signal, which actually I should have tied all along. I should have tied the reset to high, I believe. I should have tied it to high. By not having it tied to high, it might have caused some random errors. But actually, I have here another thing. I played around with the Arduino already, so that's why this stuff is in here, which actually is not really, well, I guess this is the decoder. Okay, so this is actually necessary right now, but it's totally prototypish. So that's the this is the counter. This is the line decoder, and because the line decoder is turning out inverted signals, I have here an inverter that turns the signals into uninverted mode. So to be really correct, right? And so that's why in order to connect this, I just used this 8-bit patch cable that I have here instead of wiring individual the things here nicely on the breadboard, because this is not even something that I will ultimately use. But I was wanting to anyway play around with a counter that doesn't count to 4 or powers of 2, but rather a counter that counts to 3. So I can take the reset signal and I can put it on here output 4. And because these outputs are high, these are inverted outputs here from this line decoder, so they are held high until the signal is at this point. So what you can see now is that here we're counting to 3 only. 0, 1, 2, 0, 1, 2. So it's counting to 3, which is actually nice, because now we're for the first time we have something that is not just by powers of 2. So even if I'm doing my sound thing now, so I run it real high, and now I have a squealing sound, and I actually do with a double wire that I have here. I'm only going to use the white one, right? So don't forget about the black one. I just don't want to rip these apart, because once you rip them apart, they don't get together anymore. So now I'm getting in the squealing input, right? And here I have I now have this signal divided by 3. No, it doesn't actually work like this. I think I need to change the transistor here to make the frequency even higher. But well, let's get rid of my sound module. This is not really relevant, but I found it kind of interesting that which is something that when Ben Eder was talking about his micro instruction cycles, there he actually needed only like 5 or 7 maximum, and so obviously we can save ourselves this extra pause cycle by simply putting the resulting the resulting output, feeding it back to the reset. So at this point now, I'm counting to 4, 5. 1, 2, 4, 5. See, I think I'm counting to 5 here, no? So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1. So it's counting to 5 now. And if I go up here, then I can make it count to 7. Oops, no, that's wrong. Okay, now I can make it count to 7, huh? Instead of 8. So that's kind of neat. A neat thing that I figured out. But anyway, so that's really all I can do right now. I haven't built a single register yet, nothing else. But I won't be able to get to this until maybe next week. So that's all I have to say. And how do I take this